All right, in this video, I'm going to cover section 7.1 and 7.2. Okay, so chapter 7. So we're gonna study the statistic, specifically inferential statistic. Okay, so chapter 7, the point estimations, parameters, and sampling distribution. So let me cover sec you know the sections by using my lecture note. Okay. So, so here the points estimation is nothing but the approximation. So, and the parameters are, the population mean, population variance, population standard deviations. These are called the parameters. Okay. So using the sampling, using the sample, we're gonna approximate the those parameters of populations. Okay, so let me start with the definition of statistical inferences. So statistical method are used to make decision and draw conclusion about population. Yeah, so that's a statistical inference. So the how to what is the best approximation for the population mean, population variance, things like that. Okay, so we're gonna the the we're gonna figure out the those statistical method for finding the best decision. Okay, so there's a statistical method. So now these techniques utilize the information in a sample for drawing conclusions. Yeah, so the two major area in statistical inference, so parameter estimation and the hypothesis testing. So yeah, chapter 7 cover parameter estimation, and then chapter 8 is going to cover hypothesis testing. So I told you parameter estimation, approximations of population parameters, and then drawing for the hypothesis testing, drawing conclusions about a hypothesis that is relevant to a decision. So first we wanna for example, so I mean okay, so in case that we are claiming some hypothesis, this is true. So then we want to figure out the um, how much we can how much we can trust those that hypothesis. So we want to figure out the numerical value, which is a probability, okay, for that hypothesis. What I mean, the how much we can trust that hypothesis. So finding those values is called hypothesis testing. Okay. So 7.1, point estimation. Any statistic is a random variable. All right. So what's a statistic? Statistic is all the sample. I mean the parameter sample are called the statistic. Okay. So sample mean, sample variance, sample standard deviations. These are random. These are the statistics, and the statistic is a random variable. Okay. So why the statistic is a random variable? I mean, any statistic is a random variable because look at this. So let's see. So let's say a population is given right there. Okay. So then the sample, just think about the sample mean. So sample mean x bar depends on the observations in the sample, which differ from sample to sample. So you see, depending on how we collect the sample data, the sample mean x bar will be determined, right? So sample mean x bar can be considered as a random variable. Okay, so do you see that? Not only sample mean, but also sample standard deviation and variance all depends on the what the how we collect the sample data, right? So, for example, let's think about this sample. We collect this sample here, and then we calculate the sample mean and sample mean. So it turns out the X bar is a 10.2. With the other sample, we just collect the sample in here, and then we measure the sample mean. It turns out the X bar 10.7. Okay, and then the other one for other sample, X bar is 10.4. So all three samples have the same the number of sample data, which is 10, but sample mean sample mean is different, right? They have different sample mean, the value of sample mean. So sample mean can be considered as a random variable. So now next, let's see the next one. Okay, so because statistic is a random variable, it has a probability distribution. We call the probability distribution of statistic is a sampling distribution. So sampling distribution is the probability distribution of statistic. Okay, that's sampling distribution. The next one, theta. So by the way, in 7.1, we're gonna see many terminologies we will use in chapter 7 and 8, so even 9. So please keep in mind those parameters we're gonna learn in this video. So theta is a parameter. Okay, this data is represent a parameter. For example, mu, sigma square, and any parameter of interest in population. Okay, and then x bar. Yeah, I mean, x is a random variable with a probability density function f of x, and the theta is unknown parameter. Then the what x1 through the xn. This is the set of x1 through xn is a random sample with the size n. So the capital letter X is used denoted by a random variable with f of PDF f of x, and the data is unknown parameter, and the x1 through x sub n. These are used as sample data. Okay, so this is the set of all sample data. Okay, so now then the statistic data head. Okay, data head. This statistic denoted by data head. Okay, so this is a function of x1 through xn. Is called the point estimator of data. Okay, so simply saying the h of x1 through xn, this function can be used as can be used to approximate the point estimate the approximate to unknown parameter theta. Okay, so that data height is called the point estimator of theta. Okay, so now next one, the theta head, which is a point estimator of theta, is theta head is also a random variable because it's a function of random variable. Okay, you see that theta head was h of x1 through the xn, right? x1 comma x2 comma through the xn. So which is excuse me, point estimator of theta, which is theta head is what? A function of random variable, because x sub 1 through x sub n are random variable. Okay, because we don't know, I mean, x sub 1 and x sub n are not determined. Okay, are not fixed. Okay, so it all depends on sampling method and then which data value we're gonna use as sample data in the population. So x sub 1, x sub n, 1 through xn are sample the what random variables, and the h of x sub 1 comma through xn, what this is the what the function of random variable. So data head is a random variable too. So now next one, 6. After the sample has been selected, then theta head takes on a particular numerical value theta head that is called the point estimate of theta. So point estimate of theta is nothing but approximation of theta determined by theta head. Okay, so once sample has been selected, it means that x sub 1 through x sub n are determined, selected. So using those sample data, we can find out the sample mean. Okay, for example, sample mean. So that is called the point estimate of theta, or we can say, I mean, simply that means the approximation of the mu, population mean. Okay. For example, okay. So it's example. Suppose the random variable of x is normally distributed with unknown mean mu. All right. So that means mu hat. So what's mu hat? Mu hat is a point estimator, right? Of the mean mu. Mu is a population mean, which is the parameter of population, one of the parameters of population, right? So mu hat, which is point estimator of mean mu, that is the x bar. This is sample mean. Okay. So, but what I mean, we're wondering that. Okay. So, is there any other? I mean, is there any other the what data head? Okay, data head that uh the data head for the mu head. Okay, I mean, or can say x bar sample mean is the best point estimator of the population mean mu. Okay, so we have those questions, right? So here's the answer for those questions. So this is a list of reasonable point estimator. So for the population mean mu, the mean of the of single population. Okay, so the x bar, which is a sample mean, that is the excuse me, that is the best point estimator of the population mean. Okay, so in the sigma square, the variance of single population, so sigma hat square, this is a point estimator of sigma square, right? So s square, which is sample variance, that is the best point estimator of the population, the variance sigma square. Okay, so keep in mind this. So please uh, understand the meaning of each symbol. Okay, so mu, that's a population mean, one of the population parameters. Mu hat, that is the what point estimator. I mean the symbol of point estimator of the population mean mu, and the x bar, that's the sample mean. Excuse me. The sigma square, that's the population variance, and then sigma hat square, this is the what point estimator of the population variance sigma square, and then lowercase letter s square, that's the sample variance. Now p, the letter p represents the proportion of items in population that belong to a class of interest. So for example, in the in a grocery market, then we want to figure out the proportion of the apple, for example. Okay, so you know, then the that can be that is one example. Okay, so proportion of apples, the grocery market. Okay, so then n gonna be here, the pn. This is the what point estimator of the proportion of in the population. Then n is the total number of the items in grocery market, and the x is gonna be the number of apples, okay, or number of the fruits. Okay. So now, let's see. The sample proportion, where x is the number of items in a random sample of size n that belong to a class of interest. So, yeah, so x is the n here. Yeah, I'm sorry, n is the sample size. Okay, I'm sorry for that, because it's almost impossible to figure out total number of the data in population. Okay, and then mu1 minus mu2, that's the difference in mean of two populations. And then the mu1 hat minus mu2 hat, that's going to be what difference between what the point estimator of mu1 and mu2, right? So x1 bar minus x2 bar, okay, the difference between the sample means of two independent random samples. Okay, so x1 bar minus x2 bar, that's going to be the reasonable the point estimator, okay, of the mu1 minus mu2. Okay, and then here p hat, back to the 3, p hat, that's the x over n. Okay, that is a reasonable, best. Yeah, that's actually best the point estimator of the proportion of population. Okay. So now P1 minus P2, yeah, P1 hat minus P2 hat, that's gonna be best, what? The point estimator of the difference into population proportions. Okay. So, now keep in mind this, in a mu, in the 4 and 5, so the x1 bar, x2 bar are what sample means of two independent random samples. Okay, and the P1 hat, P2 hat also what two sample proportions computed from two independent random samples. Okay, so keep in mind all the terminologies in 7.1. Now we move to 7.2. So sampling distribution and the CLT. So we're gonna learn the mainly we're gonna learn the central limit theorem. This is the one of one of the important and fundamental theorem in statistics. So statistical inference is concerned with making decisions about population based on the information contained on random sample from that population. Yeah, so we have seen that so statistic is a random variable. Why? Because the choice of the sample data, the choice of depending on the how we collect the sample, see the sample mean will be determined, right? It means the statistic will be determined. That means what population point of estimator will be determined. So the sampling is quite important, but we assume that we're gonna get sample by random. Okay, so here random sample is xi's are independent random variable. So x1 to xn are independent random variable. Keep in mind this. Okay, so it means that when we choose x2, okay, it will not be affected by the choice of x1 and other the sample data. Okay, so when you choose xi, okay, sample data xi, the that will not be affected by other choice of the sample data. Okay, so every xi has the same probability distribution. Yeah, keep in mind this. That's the random sample. And the statistic is any function of the observations in a random sample. I told you what's the statistic. Yeah, statistic. What? See, what sample statistic is random variable. Statistic means what? The sample mean and sample variance sample. All the what sample, for example, sample mean and sample variance, sample standard deviations, that can be considered as a function, right? Function of observation. Here, observation means the sample data, okay? Can be considered as a function of observations. So to calculate the sample mean, we have to what? Apply. We have to use the the formula sum of all the sample data divided by number of the divided by sample size, right? So that formula can be considered as a function of the observations x sub 1 to x sub n, okay? So now we can say that the statistic is a function of the observations, or can say statistic is a function of the sample data in a random sample. So now the by the way, oh yeah, it's a new movie. Okay, so sampling distribution, I told you was this probability distribution of statistic. Okay, so for example, we can find out sample mean x bar. I mean, uh, for many random samples. Okay, so we can the what we can create the so many random samples, right? Maybe 100 or maybe more than 100. Okay, then we're gonna find out sample mean for each random sample, and then the visualize. In drawing the probability distribution of that sample mean. That's gonna be one of the graph of sampling distribution of X bar. Okay. So now next one. So give me a second. So I think Let me show the example of sampling distribution in the textbook. Okay, so here's section 7.2 textbook. Okay, so now, yeah, we're gonna see this one after the studying the center limit theorem. But let's take a look at this. So this table shows the sample, observations with n sample size 10. Okay, so but you see that here, what explore for each. So now is this one in what the each column number 1, 2, 3, 4 means sample number. Okay, so sample one, sample one, and sample two, and sample three. For each sample, there are 10 observations, right? So here, vertical number under here, the row number 1, 2, 3, 4. 1 second. So here 1, 2, 3, 4, 5, 6, 7, 10. That means the observation number. The column numbers. That's the sample number. Okay, right. I mean the set of sample number. Okay, so how many the sample we collected? I think 20, right? You see the 20 right there. Okay, so see, then for 20 sample, the set of samples, we calculate the X bar. Let's see, X bar right there. Right. Okay, and then now we plot the what? Give me a second. Oh, all right, X bar. So now we plot the graph. So here vertical line represents percent of normal probability. Okay, and then the the horizontal line represents sample mean X bar. Okay, so now then we're gonna calculate the how many times we got the that sample mean. Okay, how many times we got this sample mean, right? So we calculate the percentage, right? So we throw that. We just throw the points for each sample mean. Okay, that can be considered. That is one example of sampling distribution. Or this is called sampling distribution too. This is also sampling distribution. Okay, so now then, now back to the. Give me a second. Let's back to the lecture note. Now here, so center limit theorems. So if we are sampling from a population that has an unknown probability distribution, the sampling distribution of the sample mean, schema sampling distribution of sample mean. I'm not saying the sample mean. Okay, sampling distribution of sample mean will still be approximately normal. It means that the distribution, a probability distribution of sample mean will has the bell shape. Okay, it means the probability, distribution of the sample mean will be normal distribution, will follow normal distribution. And then what's the mean? And then mean gonna be mean of the sample mean, right? Mean of sample mean gonna be equal to the population mean mu, and then variance will be equal to sigma square, which is population variance over sample size. Okay, if the sample size n is large, which normally we um, we say the n is greater than 30, then CLT will almost always apply. Okay, so keep in mind the center limit theorem is about the sampling distribution of sample mean. Okay, so or can say probability distribution of sample mean. So if the population, okay, if n is a sample size is greater than 30, then probability distribution sample will be approximately normal distribution. Okay. So now, next one. What if the population is a normal distribution? That means what? Then the sample distribution, sample mean, definitely sampling distribution of sample mean will be a normal distribution. Okay, with the mean is mu and the variance sigma square over n. Okay, so but what if a population mean a population the population is not a normal distribution? Then but if n sample size n is greater than 30, then sample link distribution of sample mean will be normal distribution. Keep in mind this. And then if x sub 1 through xn is a random sample of size n taken from population with the mean mu, variance sigma square, and if x bar is sample mean, then see the g-score? We learned that, right? G-score, this is the, what's this? This is the random variable in normal distribution, right? Then g-score is x bar minus mu over sigma over square root n. Sigma over square root n, this is the sample the standard deviation, right? So here it means the sample distribution of the sample mean can be transformed to the standard normal distribution. So z-score, this is the random variable in the standard normal distribution. Okay, so this is example 7.1. So look at the, let's just read the question in the example 7.1, 7.2 in the textbook, okay? So here's key point. So mu is 100 omega, and the sigma is, this is 7.1 is about register, okay? So please read the problems, okay? And then back to this lecture video, okay? So mu and the sigma and the sample size given. So mu is a sample, population mean, and the sigma is a population standard deviation, right? Now mu x sub x bar, this is the sample mean of, the mean of sample mean, sorry. Okay, mean of sample mean is also 100. And then, in 7.1, the problems assume that the population, let's see, give me a second. So the problem says the population is normally distributed, okay? So now then, regardless of what the sample size, the mean of sample mean, which is mu sub x bar denoted by mu x sub bar, is 100, which is equal to mu, the sigma sub x bar, which is the standard deviation of the sample means, okay? Is sigma over square root n. Excuse me. So which is 10 over 5 is 2. Okay. So now then what? So now since the by the CLT, we got the mu x bar, sigma x bar, right? And then also then we can find out the probability that we're gonna get sample mean the 95, okay, in the sample distribution of this sample mean, okay. So this is how to calculate this, right? So, but once you get the figure out mu x bar, sigma x bar, you can use calculator to figure out the probability that we get 95 sample mean, okay, using calculator, okay. So this example 7.2, see, f of x is a continuous uniform distribution, okay. So now it means that f of x is a constant function, okay. So now then let's see example 7.2. I think I need, yeah, give me a second. All right, so see 7.2. Suppose that a random variable x is a continuous uniform distribution. You see that f of x is defined as a piecewise function. So f of x equals 1/2 when x is between 4 and 6, otherwise 0. Define the distribution of the sample mean of random sample of size n equals 40. Okay, so you see that sample size is greater than 30. Okay, then we can use central limit theorems. So the mean and variance of x are mu is 5 and sigma square is, why is it 5? Because what? Can you see that? Because mu, I mean, now there, so mu is what? Look at the lecture note. Because for the what? The uniform distribution, mu is a plus b over 2. Okay. So which in this case, a is a left n number and then b is a right n number of domain. Okay. So now the a must be 4 and the b must be 6 because the what beyond the, you know, I mean, the out of that inner number 4 to 6, f of x is 0, right? So we only consider the inner number 4 to 6. So since mu is a plus b over 2, this is formula for the continuous uniform distribution. A is 4, b is 6, so we're going to get 5. And then sigma square is a b, we can calculate b sigma square as b minus a square over 12. Okay. All right. So now then we got this. So then using central limit theorems, we can calculate the mean of sample mean and then standard variance of the sample mean. I mean mu x bar and the sigma x bar square. Okay. So the central limit theorem indicate that the distribution of x bar is approximately normal with the mu x bar is 5 and the variance is what? Sigma x bar square is a sigma square over n. Because n is 40, sigma square is 1/3, so we got 1/3 of 40, which is 1 over 120. Okay. So now then, the graph of the, since what? By central limit theorem, what? The probability distribution of sample mean, that is called the what? Sampling distribution of the sample mean, right? So sampling distribution of sample mean gonna be normal distribution approximately. So you see the graph right there. Let's see this graph. Okay, you see. Okay, this is the sampling this graph, sampling distribution of the sample mean of this problems, and the mu x bar is 5, and then standard deviation sigma x bar gonna be 1 over 1. I think it should be. Give me a second. I think the square root of 1 over 120 is just a typo, right? Okay. So now, yeah. Okay. So now, see the back to. Give me a second. All right, so now in the approximate sampling distribution of difference in sample mean, okay, so we assume that we have two independent populations, mu1, mu2, and sigma 1 square, sigma 2 square, and the x1 bar and x2 bar are sample means of two independent random samples of size n1 and n2. Then the sampling distribution of z-score, which is calculated as like this, x1 bar minus x2 difference between x1 bar, x2 bar minus difference between mu1 bar, mu1 and mu2 divided by square root of sigma 1 square over n1. This is what the sigma, what the the variance, right? Sigma 1 square over n, this is variance of the sample mean x1 bar, the sigma square over n squared. This is a sample, I'm sorry, the variance of sample mean x2 bar, okay? Some of them, square root some of them, okay? That is approximate standard normal, okay? And this is not just normal, okay? Standard normal, okay? That's interesting. If n1 is greater than 30 and both n1 and n2, both sample sizes are greater than 30, okay? If two populations are normal, then the sampling distribution of Z is exactly normal, okay? See, okay? So the schema is this. So let me, see, give me a second. Yeah, so maybe we'll see the, let me stop here and then we'll see the example of this problem, this one in the assignment, okay? So next time, and then I'll cover 7.3, 7.4. Okay, that's for today.